Hello everyone. Starting from part 14 up to this video, the common point is in all these cases the nucleophile that are used in nucleophilic addition to carbonyl all are similar kind. So what is the similarity? The similarity is all of these nucleophiles are carbon, that is negative charge present on carbon. Okay, so benzoin condensation, this reaction also under this category, that is addition of carbon. So let's see what is benzoin condensation. So benzoin condensation, basically it is not called as benzoin addition, it is called as benzoin condensation, though mostly by condensation what we understand that there is removal of some small molecule like water. In this case there is no such thing, but mostly it is called condensation, but better from the mechanistic point of view we should call it benzoin addition, because here addition reaction is taking place. So in this scheme I have taken basically two same molecules. This is also aromatic aldehyde, this is also aromatic aldehyde, but what is the difference? Both are not in same color, that means their roles are different. So one is acting as donor, another one is acting as acceptor. Though they are same molecule, still their roles are different, and the catalyst that we are using is Cn-. Okay, that is cyan. So from the donor part we are getting this portion, that is CO, ArCO, and from the acceptor side we are getting ArCHOH. Okay, now this term benzoin, it is actually coming from acyloin. Acyloin means α-hydroxyketone. That is, this is carbon, that is with respect to keto group, this is alpha carbon, so α-hydroxyketone. So this structure, that is actually called acyloin, but as here we have taken aromatic ring, so that is if this aromatic ring is benzene ring, suppose if it is pH, then it will be called benzoin because of the term benzene. Okay, so acyloin is COCOH alpha-hydroxyketone, and here also this structure is present, so that is why it is called benzoin when Ar is pH, and this is catalyst, so this is regenerated. So reaction involves aromatic aldehyde, okay, and catalyzed by cyanide ion. So this catalyst is very specific for this reaction, and why it is so we will also discuss that. The reaction product is aromatic acyloin, so benzoin if Ar is pH. Reaction is completely reversible, so here we have used reversible sign. So from donor aldehyde carbanion is generated. Our nucleophile is carbanion, so this nucleophile is generated from donor aldehyde, so that is why we are calling it donor. And another one which is acceptor, that means it will accept the electron charge density from the donor, so that is why we are calling it as acceptor aldehyde. Okay, so their roles are different. Now we will see the mechanism. The first step is nucleophilic attack of Cn-, so negative charge over carbon. So this Cn-, it will attack carbonyl carbon, and there will be negative charge over oxygen. Now this hydrogen which is attached to carbon, this proton will be shifted to oxygen. So now we are getting carbanion, and here we have OH. So this is also one kind of ampolla. Normally when it is carbonyl group, this carbon is electropositive, but here we have generated negative charge because this proton is shifted to O-. So that is why there is reversal of polarity, which is also known as umpolam. And here resonance is possible because Cn group is present. So COH negative, C triple bond N. So this negative charge, it can undergo resonance like this. So this is another resonance structure. So this carbanion is actually very stable because of this type of resonance. So now our donor is ready. This is donor. Okay, donor carbanion. Next, now this pink colored aldehyde, this is acceptor. So nucleophilic addition of carbanion will take place. This negative charge will attack this carbonyl carbon, negative charge over oxygen. Now again there will be proton shift. So this hydrogen, it will be shifted to this oxygen. And what is the reason behind why it is happening? Because if there is no negative charge, then Cn cannot be removed. So now there is negative charge over this oxygen and there will be loss of Cn. Because it is pushing the electron density, we are getting back CO. So from the structure of the final molecule, we can easily identify that which part is coming from donor molecule and which part is coming from acceptor molecule. So CO, that is alpha hydroxyketone, it will be produced. So the group which is attached to carbonyl carbon, that is this Ar, it is basically coming from donor, and another part which is attached to CHOH, that is coming from acceptor. Here both are same molecule, but it may be we have taken two different aromatic aldehyde, that is crossed benzoin condensation. So in that case these two groups will be different, but from the final structure we can easily understand which part is coming from acceptor and which part is coming from donor. Okay. Now why this catalyst is so unique for this reaction? Why we do not use any other catalyst? So there must be some reason. First of all, it is a good leaving group. So in the mechanism what we have seen in the last part, there is loss of Cn. So if it is not good leaving group, then this removal of Cn, it will not take place easily. So the catalyst must be very good leaving group. And the most important thing is it is a good nucleophile, because the first attack that we have seen in the mechanism, the first attack to carbonyl carbon, if it is not very good nucleophile, then that attack is not possible. Okay, so Cn minus, it is attacking aldehyde. So this attack, it is possible, it is facile because it is a good nucleophile. It increases the acidity of the CH bond and stabilizes the carbanion. So the carbanion jet that is produced after proton shift from carbon to oxygen, with this carbon, Cn is also attached. Now as it has electron withdrawing capacity, so it can increase the acidity of this CH bond. So this, the hydrogen which is originally attached to carbon, that will be easily shifted to O minus. So now this carbanion is stable because Cn minus is stabilizing this carbanion. Okay. So these are the main reasons for which Cn minus is the unique catalyst for this reaction. The reaction can be performed in a mixture of two possibilities. One is two aldehydes. Now these two aldehydes, it may be different or it may be same. So suppose we have RCOH, another one is R prime COH. Suppose it is donor, it is acceptor. So what should be the structure of the final product? Because from the donor part we will get CO. So it will be RCO, then CHOH. With CHOH, acceptor R group will be attached, that is R prime. So this is from acceptor, this is from donor. Okay. And another possibility is, now remember how to understand that among these two aldehyde, which one will act as donor and which one will act as acceptor. Now it is easy to understand, because the aldehyde where the electropositive character of carbon is high, that will act as donor. Why? Because donor is generated by this attack of the cyanide ion. Okay. So if cyanide ion, it is acting as nucleophile, so the electropositive character of carbon, if it is not very high, then Cn minus, the attacking tendency will be less. So in this among these two aldehyde, suppose the aldehyde one, its activity is high depending on this R group. Okay, so obviously Cn minus will attack at this carbonyl carbon, not the aldehyde to carbonyl carbon. Okay, so there will be generation of O minus first, then from O negative it will be C negative, that is the carbanion, and that is actually our donor, which will act carbonyl carbon of aldehyde 2. So this is one possibility. Another possibility is, suppose we have aldehyde and another one is ketone. So obviously the aldehyde will act as donor. Why? Because here electropositive character, if we compare, obviously aldehyde, in case of aldehyde, the electropositive character is high, because here we have only one alkyl group and here we have two alkyl. Actually it is aromatic. I have written R, better if I write AR it is better, but it is aldehyde, so obviously aldehydes are always having more electropositive carbon. Okay, so that is why donor will always be generated from aldehyde and acceptor will be generated from ketone. Okay, so here the product structure will be, first of all we will write alpha hydroxyketone, then from acceptor we, sorry, here actually hydrogen will not be present. This is R prime, because in acceptor we do not have any H and this side we will have R. Okay, so in this way we can easily draw the final product. So the more reactive aldehyde will eventually act as donor, that is as nucleophile, if there is two different types of aldehyde. Similarly, if it is the mixture of aldehyde and a ketone, it is always the aldehyde that will act as donor, that is nucleophile. Now we will see some examples of mixed benzoin reaction, that is now we are two different types of aldehyde. Okay, so we will call it mixed benzoin reaction or crossed benzoin reaction. So in the first example here, this is actually aromatic aldehyde, the first one, right? And this is aliphatic aldehyde. So in presence of Cn minus, which aldehyde, that is Cn minus will attack which one? Suppose this is A, this is B. So Cn minus obviously attack the aliphatic CH2, that is compound B. Now why it is so? Because here the double bond character of carbonyl is less, because this carbonyl can take part in resonance with the pi bonds of benzene ring, but that is not possible in case of this aliphatic CHO. So that is why here Cn minus will attack, and as a result it will act as donor, and this is acceptor. So if it is donor, that means the CO part, this is alpha hydroxyketone. So the CO part that will be generated from the aliphatic aldehyde. So that is why CO is written with it. We have CH2, CH2PH, and in the OH part, that is alpha hydroxyketone part, alpha hydroxy part, that is this portion, there is attached PHOA. Okay, so in this way we can easily write the product structure. Next example. Now we have aliphatic aldehyde, the first one. Suppose this is 1, this is 2, and 2 is actually beta keto ester. This part is ester, and it is alpha keto ester, not beta keto ester. This is alpha position, so at alpha position there is keto, and among these two, actually here we do not have mixture of ketone or aldehyde. This is to some extent different. Here we have mixture of alpha keto ester and another one is aliphatic aldehyde. Okay, so Cn minus, it will attack that carbonyl carbon which is more reactive. Now which is more reactive? Obviously here this aldehyde is more reactive. Actually one aldehyde is there, another one is not aldehyde. So the aldehyde will be more reactive because here first of all it is attached to benzene ring, right? So obviously the double bond character of this carbonyl carbon, it will be less, and also steric hindrance is present because this large group is present here. So Cn minus, it will prefer to attack at this carbon. So the carbonyl compound where the first Cn attack happens, that molecule actually acts as donor. So our donor is first one, acceptor is second one. So now this part is alpha hydroxyketone part. So with in the keto part, that is this portion, this is coming from donor, and this part it is coming from acceptor. Okay, it may be confusing that now we are using some aliphatic aldehydes, okay, because at first slide we have said that it is aromatic aldehyde. Actually mostly it is observed for aromatic aldehyde, especially benzaldehyde. That is why the name of the reaction itself is benzoin condensation, okay, but that does not mean we will not observe it in case of other molecules where this similar kind of mechanism is possible, okay. So that is also possible, but mostly it is observed for aromatic aldehyde, okay. And the last one, now this is very interesting. Why? Because here both the carbonyl carbon, it is present in the same molecule, okay. And another thing is, this is actually aldehyde and this part is actually ketone. So obviously aldehyde will act as donor, because aldehyde compared to ketone, it is more reactive. But there is another contradictory factor, and that factor is this aldehyde is attached to benzene ring. So as it is attached to benzene ring, there may be conjugation possible like this. So double bond character of aldehyde will be less, right? So this is another point which is actually decreasing the electropositive character of aldehyde. Though these two factors are opposing, but still it is aldehyde. So that factor actually win over the other factor, okay. So we have to consider that point, that among aldehyde and ketone, always aldehyde carbon, its electropositive character will be high. So Cn minus, it will attack here first. So the carbanion that will be generated at this carbon. As a result, we are getting α-hydroxyketone. So this α-hydroxyketone, the keto part, that is this part, it is coming from this donor side. So this side is basically donor, this part is acceptor, okay. So if I number the carbons 1, 2, 3, 4, it is always I think it is convenient always to put numbers on the carbon, because when we will draw the cyclic structure, it will be easier. So it is 1, 2, 3, 4, okay. So this is donor side, this is acceptor side. So these are the three examples of cross benzoin reaction. Another cross benzoin reaction, but this is you can say one type of application, because by this method we can generate polynuclear compounds. So here we have aromatic aldehyde. So this is aromatic aldehyde, two aldehyde groups are present in benzene ring, and this is aliphatic, okay, glyoxal. Now Cn minus, obviously both are aldehyde, but which aldehyde is more reactive? Obviously this one is more reactive, glyoxal. So Cn minus, it will attack at this glyoxal molecule. So the mechanism will be two Cn minus, we will take, negative charge over oxygen, sorry. Now this proton will be shifted to O, that is proton transfer, and there will be negative charge over carbon. Now the another molecule, HCO, this negative charge will attack, and we will get 6-membered. O minus, O minus, and with this carbon we have OH, Cn, OH, Cn. Now again there will be proton transfer, so these two protons, it will be transferred to O negative. So now it is OH, Cn, O minus, So O minus will, the negative charge, if it is pushed, it will be, Cn will be removed. Okay. So finally we are getting now here aromatization will take place. Okay, because if that is the driving force, if it is aromatic, it will be more stable. So this hydrogen, it will take part in reaction in this way, and carbonyl will be converted to OH. So finally what molecule we will get? This one, right? So I will draw it here. The two new double bond that will be produced at this position, and total 4 hydroxy. Okay, so this is the application. Now another application we will see. Actually in this slide you can see so many reactions. So this is the product benzoin α-hydroxyketone. Okay, and this α-hydroxyketone, this is actually the product of benzoin condensation or benzoin addition reaction. Now this product we can utilize it for different purposes. Okay, so here we have used different types of reducing agent. All are reducing agent, but their products are not same. Okay, so different types of products we are getting. In the first case we are getting 2 OH group at 1 and 2 carbon. Then we are getting COCH2. This is dihydroxy. Here we are getting CH2 CHOH, and the last one, this is CH2 CH2. Okay, so depending on our requirement, what type of product we want to get, we have to use different types of reagent. Now in the left hand side, if you see, we are using HNO3 first, which is acting as oxidizing agent. So this CHOH, it will be converted to CO. So this molecule is known as Benzyl. Now this is the reaction condition which is actually very famous. It is known as benzyl benzylic acid rearrangement. So this molecule is benzyl, this is benzylic acid. So these molecules are actually very important. Okay, synthetically if we see from synthetic point of view. So starting from this benzoin we can make benzyl, and once we have made benzyl, we can also make benzylic acid, okay, by rearrangement. And benzyl, when reacts with this diamine compound, there will be formation of this type of ring. Okay, so these are the applications. Finally we will see one problem, and here two molecules we have, both are aromatic aldehyde. In the first case there is NO2 group at 4 position, in the second case there is NMe2 group. So we have to explain why para-nitrobenzaldehyde, that is the first molecule, and the second molecule para-dimethylamino benzaldehyde, they do not undergo Benzoin condensation. Now what is the reason behind that? So first of all, this molecule, I am directly writing the donor carbanion. Okay, so here the donor carbanion will be C minus Cn, that is after attack of Cn. I am jumping some of the steps. So this is OH, N double bond O, O minus N plus. Now this carbanion, why it cannot act as donor? It can't act as donor because the nucleophilicity of this carbanion will be decreased by this type of resonance. So NO2, it has minus R effect, and because of that the negative charge, it will be shifted towards the benzene ring. So carbanion will not be present, so it cannot act as donor. Okay, otherwise if you consider the fast attack by Cn minus, it will be facile. Why? Because NO2 is electron withdrawing group, so double bond character of carbonyl carbon, that is the electropositive character, that will be very high. So this is the reason for the first molecule para-nitrobenzaldehyde. And what about the second molecule? First of all, this is electron donating group. Here actually two reasons you can consider. So because of this donation, here double bond character of aldehyde will be decreased, because if we draw the resonance structure, double bond character of carbonyl, carbon is now reduced, NMe2, hydrogen positively charged. So the fast attack by Cn minus, that will be very difficult. And somehow, even if the carbanion, if it is generated, it will be like this C minus Cn para position NME2. Suppose if this donor is somehow generated, but the problem is now another molecule which will be acceptor, it cannot act as a very good acceptor. Why? Because here the double bond character of carbonyl carbon, that will be decreased because of this donating effect of NME2. Okay, so double bond character is reduced, electropositive character of this carbon is reduced, so it cannot act as acceptor. Okay, so this is the problem with the second molecule. The first molecule cannot act as donor, second molecule cannot act as acceptor. Okay, so if you find the video helpful, please like, share and subscribe. You will find all the important links in the description box, and also for other Carbanion related nucleophilic addition to carbonyl, please click on the link appearing on the screen, and this is a link for playlist. Okay, I'll meet you in the next video. Thank you for your time.